Hey there, welcome back to A Slice of Physics. We're now ready to get some additional practice working with capacitance, charge, and potential difference. We'll take some examples and see how these quantities change in various situations. Here's the example we're going to work with today. It says that a parallel plate capacitor with paper between the plates, and it gives us the dielectric constant of the paper as 3.0, is connected to a 9-volt battery. When fully charged, which means the battery is given enough time to charge the capacitor, the plates of the capacitor will have charges of plus and minus 54 nanocoulomb. One plate would have positive 54 nanocoulomb, the other plate would have negative 54 nanocoulomb. So then it asks, what is the capacitance of the capacitor? Next, it says that the battery is disconnected and the paper is now removed from between the plates. Then it asks, in this new situation, what's the capacitance, what's the charge on the plates, and what's the potential difference across the plates. And I've listed the relevant equations and constants over there, but you know that the first thing you always want to do in any physics question is draw a picture. So let's say here's our parallel plate capacitor. It's got a dielectric between the plates that's got a dielectric constant of 3.0. And it's connected and fully charged by a 9-volt battery. And it also tells us that the charges on the plates are these values. So I've got positive charges on the top plate because that's the positive end of the battery. The negative end of the battery is at the bottom, so the negative charges will be on the bottom plate. And this plus or minus 54 nanocoulomb simply tells us that on the positive plate we've got plus 54 nanocoulomb, and on the negative plate we got minus 54 nanocoulomb. And then it asks us for the capacitance of the capacitor. Well, can we figure that out? Let's see. So we want to get the capacitance of this capacitor. We know the delta VC, the potential difference across the plates of the capacitor. That is 9 volts. Remember, when a capacitor is fully charged, the delta VC, which is the potential difference across the plates of the capacitor, will become equal to the potential difference of the battery that was doing the charging. And we're also given Q in this case, and that's 54 nanocoulomb. Remember, the positive plate has a charge of plus Q, the negative plate has a charge of minus Q, so this Q value is simply the number part of the charge without the sign. So do we have enough information to figure out the capacitance of this capacitor? Well, some of you may now be wondering, hey, I don't know the area of the plates, I don't know the distance between the plates, and I was told before that the capacitance only depends on the physical properties of the capacitor and does not depend on the charge or potential difference. So how do I figure this out without knowing the area and distance between the plates? The thing you got to remember is both of these equations always work. What we meant by saying that the capacitance doesn't depend on charge or potential difference is that simply by changing charge or simply by changing potential difference, you can't change the capacitance. You can only change capacitance by changing its area, dielectric, or distance between the plates. But this relationship is still valid. And that's how we first met capacitance. We said capacitance influences the amount of charge that you need to separate in order to get a known potential difference. Well, knowing that charge separation and knowing the potential difference, we certainly can use this relationship to figure out the capacitance. So in this case, I would have capacitance equals Q over delta VC. So that would be 54 times 10 to the negative 9 coulomb divided by delta VC was 9 volt. And this gives me 6 times 10 to the negative 9 farad. Coulomb over volt is farad. And I can write this if I want as 6 nanofarad. So that's our answer to this first part here. We're done with that. Next, it says that the battery is disconnected and the paper is removed. So once again, we got to draw a picture of that situation. So we got the capacitor here. It's no longer connected to a battery. So let's say these wires are snipped and the battery is gone. And now, because the paper is removed and there is just air, the dielectric constant becomes 1.0, which is air's dielectric constant. And I call this kappa 2 just to differentiate it, and let's call this kappa 1 as the initial condition. Okay, we got three things to figure out now. We got capacitance, charge, and potential difference. Is there one of these that we can figure out rather easily? is there one of these that doesn't change from before? Well, we know that the capacitance changes because we have changed kappa, so we have changed how the capacitor is built, so capacitance is going to change. Let's see if charge or the potential difference across the plates remains the same. Well, what happens when we cut this wire? When we break the circuit after the capacitor was fully charged, we have trapped those charges on the opposite plates. So these charges have nowhere to go. And so they're just going to stay there even after we cut this wire or cut that circuit. So I'm still going to have plus 54 nanocoulomb here and minus 54 nanocoulomb here. That tells me that Q remains unchanged at 54 nanocoulomb. Next, even though I know that capacitance has changed, I can figure it out. Remember from our previous video that I can write these relationships. Capacitance 1 equals kappa 1 epsilon naught A over D. And I'm writing it this way because the only thing that changes is this dielectric constant. The area doesn't change and the distance doesn't change. So I don't call it A1 and D1 and A2 and D2. They're both the same. And I got C2, this new situation, as kappa 2 epsilon naught A over D. Same area, same distance, but a different dielectric constant. So as I did before, I can divide these equations. I can write C2 over C1 equals, C2 was equal to kappa 2 epsilon naught A over D divided by C1, which was equal to kappa 1 epsilon naught A over D. I can get away with doing this kind of equation division because this numerator here, C2, equals this numerator, and this denominator here equals this denominator, and any fraction where the numerator equals the numerator and denominator equals the denominator, the fractions are also equal to each other, so this equal to works. And then lastly, when I divide two fractions, I just write the top fraction first and multiply it by the reciprocal or the inverse of the second function. So I flip the second function and change the division to a multiplication. And then as a last step, I cancel the common terms. Epsilon naught A here cancels this, D here cancels this. So this simply gives me C2 over C1 equals kappa 2 over kappa 1 in this case, since none of the other factors change. And I know kappa 2 over kappa 1, so I can write this as C2 over C1 equals kappa 2 is 1.0, kappa 1, the original value, was 3.0. So this gives me C2 equals 1 over 3 times C1, and I know C1. That was the original situation over here, so that was 6 nanofarads, 6 nanofarad, and this simply gives me 2 nanofarad. So now I've got the new capacitance of the capacitor. So I've done this part, and I already figured out the charges on the plates didn't change, so I knew that. So my last thing was to figure out the potential difference across the plates in this new situation. Well, I can go back to this second relationship over here, which tells me that C equals Q over delta VC. And when I rearrange this, I can say delta VC equals Q divided by C. And I know both of these. I know that Q is 54 nanocoulomb, which I'm going to write it like this, times 10 to the negative 9 coulomb. And the capacitance is 2 nanofarad, so that's 2 times 10 to the negative 9 farad. The 10 to the negative 9 will cancel each other. 2 goes into 54 27 times. Coulomb over farad is volt, so I get a potential difference of 27 volts. So let's quickly review what we did here. We had the capacitor fully charged and figured out what charges were deposited on the plates, and that enabled us to calculate its capacitance. Then we disconnected the battery, which trapped the charges, so we knew that the charges didn't change. And we removed the paper, which changed the dielectric constant, which changed the capacitance, because now the capacitor is built differently. And we could use those ratios to figure out the new capacitance, and then we used the new capacitance and the charge to figure out the potential difference, and saw that the potential difference between the plates will jump to 3 times what it was before, simply by disconnecting the battery and removing that paper. In this slice of physics, we looked at how capacitance, charge, and potential difference between the plates change in various situations. We realized that it's important to understand each situation and figure out what changes and what does not. And here are 3 rules that I think will help you approach problems like these. The first rule is that you got to remember that capacitance changes only when kappa, A, or D are changed. Otherwise, it remains unchanged. Second, when you disconnect the battery and don't have any circuit that's connecting the capacitor, the charges on the plates are trapped, so they cannot change. And third, when you do connect a battery to a capacitor and give the battery enough time, the battery will fully charge the capacitor and only stop working when the potential difference across the plates of the capacitor are equal to the battery's potential difference. Thanks for watching.